number 7. How many chlorides for each of these? Chloride is an ion. And so when we look, there are a couple of ways of looking at this. Are these 3 chlorines here chloride ions? No, actually just 2 of these are. These 2 chlorides are ionically bonded to this cation. However, this chlorine is not ionically bonded. In a complex, what types of bonds form when we have electron pair donation? A coordinate covalent bond. So this chlorine is not ionically bonded. This chlorine is actually covalently bonded with cobalt. It's a weird bond. It's a weird bond which we just described as being best described using MO theory, which we aren't going to get into. And so it's actually a covalent bond. And so normally a metal, non-metal forms an ionic bond, but these complexes form coordinate covalent bonds here. And so when we're looking at how many chloride ions there are only 2 chloride ions. So I wanted to talk a little bit more about problem number 7 here, because I skipped Werner. You know, Werner won the Nobel Prize. For this. Because what was the oxidation state of the cobalt here? Well, let's go back to that. 2 plus. Anybody else have a 3 plus? So if it were 2 plus, ammonia or neutral. Actually, this is a typo. Sorry about that. This is not NH. It's supposed to be NH3. NH3. It was supposed to be. I think I screwed this up when I copied this. All right. In fact, it was supposed to be. Let me fix this. Now I realize why it came out weird. This is something I copied and pasted. From the book. Didn't look at it carefully enough though. But anyway, we could do it like this. So if I have a cobalt 3 plus, and how many chlorides would I need to balance out the charge? 3 chlorides. So 1, 2, 3. And what does that make? It makes cobalt 3 chloride. Cobalt 3 chloride, like all ionic compounds, are solids, basically. There are some ionic compounds with fairly low melting points, but they're still solids. And when we have an ionic compound like this, what is the structure of the ionic compound? Crystal lattice? Ionic lattice? Yeah. So we have an ionic lattice, and let's try to draw out the ionic lattice. I'll draw out a cobalt, and is a chlorine bigger or smaller than a cobalt? So if I draw out 2 atoms like this, which one would you suspect would be the cobalt, and which one would you suspect would be the chloride? Cobalt 3 plus and chloride minus.
Would chlorine be the bigger one since it has... I don't know.
You're right. Chlorine should be the bigger one because it has...
A larger outer shell or something like that?
No. No, actually cobalt has a greater outer shell. The outer shell on chlorine is in the 3rd shell. The outer shell on cobalt is also in the 4th shell. It's the 4th shell when it's neutral. No, they get smaller going across. they get bigger going down and smaller going across. But you just have to remember this. Anions are bigger than cations. That's a rule. There are a few exceptions to the rule, but for the most part, it's a pretty decent rule. Anions are bigger. And why are anions bigger? Anions are bigger because when you gain an extra electron, you have the same number of positive charge, same number of protons. And so now you have more negative charge to hold on to it. And so there's another rule. And the other rule is that anions are X times bigger than their parent. So if I have chlorine, then chloride is going to be X times bigger. What is X? This is a rule, so it's not perfect. Well, I mean, how many times bigger? Is it twice as big, 3 times as big, 4 times as big? How many times bigger is an anion typically? So if I know the size of a chlorine atom, let's say it's this big, the chloride atom is going to be about how many times bigger? Half times? 2 times bigger. It's going to be about twice this size. And so we look up the atomic radius of chlorine. It's about 100 plus, and then this would be about 200 plus. The same thing happens like sodium. Sodium has a radius of about 100. Sodium ion has a radius of about what? How many times smaller? Or it's going to be, let's say, half as big, a quarter as big. What is it? It's going to be about 2 times smaller, half as big. So it'd be about 50. And so cations are usually smaller. The few exceptions are the very largest cations, like cesium cations, the biggest cations you can have, and the very largest anions. The very largest anions would be like iodide. Would be the very largest. So when I draw out a structure like this, we look at it electrostatically. So a positively charged ball is going to want to have as many negative charges around it as possible. So we draw some kind of lattice like this. So each cation is going to try to maximize the number of anions that surround it. And each anion is going to try to maximize the number of cations around it. And then eventually we draw an ionic lattice. Do you guys remember these? Basically. And when we look at the ionic lattice, like if we have a lattice of chlorides like there, then there's these little holes, and these little holes are where the cobalt goes in. Do you remember the different shapes of the holes that we had in Chem 1A? You remember them, Kat? What were they? Remember talking about it? Mm-hmm. Trigonal was one. Trigonal is the smallest. It's so small that trigonal holes we don't really worry about too much. We worry about the bigger ones. The bigger ones would be the octahedral. Octahedral is the bigger one, but it's not the biggest. Do you recall what the biggest hole is in a lattice? So if I have a lattice of chlorides and I stick this into the biggest hole in chloride, like a cesium, if I put a cesium atom in there, then it's going to form the cesium chloride structure. And it's called a cubic hole. Cubic hole is the biggest. Then the next biggest would be so cubic hole is the biggest. Then the next biggest would be like when we did the crystal lab, you fit the blue marble fit in this hole. And the pink marble fit into the smaller one. Do you guys remember that? Maybe you guys built it or you didn't build it? You didn't build it? Okay. We built this, remember the sodium chloride lattice? This was a lattice of chloride ions, a face-centered cubic lattice of chloride ions with the sodium ions in the octahedral holes. And then we had tetrahedral holes, which is the zinc blende or the zinc sulfide structure. This is important for you geologists. Geologists need to know crystal structures quite well. But anyway, we have these little void spaces. These are called holes or void spaces. So either we can fit a cation in there or we can fit other stuff in there. And so if we have cobalt-3 chloride, this is called anhydrous. Anhydrous means what? There's no water. And what happens is we have humidity and air. If there's humidity and air, that means there's gaseous water, water vapor and air. And what happens is the water vapor can like wiggle its way inside the lattice. So if we have a water molecule that kind of wiggles its way into one of the voids or these are called interstitial sites, one of these little sites here in the lattice, then we can get water in there. And there's going to be attraction because water is polar and these ions are very polar, negative or positive. And so the water can squeeze in there. And then what happens is we can form hydrates. And so a hydrate would be something like this, cobalt-3 chloride dot 3H2O. And this is a solid still. So we'd call this, what would we name that? We call it cobalt-3 chloride blank hydrate. Trihydrate. Cobalt-3 chloride trihydrate. What's the max number of waters? Well, it depends. We could form monohydrate, dihydrate, trihydrate, tetrahydrate. What's the max number of water? The max number of waters depends on how many you can fit in there. Typically the max is like 6. Sometimes it's lower than 6. Sometimes we can only fit 4 in there. Sometimes we can only fit 2. But it also depends on the relative humidity of the air. If the air is not very humid, you aren't going to fit as many. If it's really humid, then you can get lots of water. If it's totally dry, no water is going to get in there. Maybe you'll get a monohydrate in that case. But we can dry hydrates by just throwing them in the oven. We throw this in the oven and the water molecules are kind of vaporized out of the solid. And so that's one way of doing that. But why does water squeeze in there in the first place? Because water is polar. What else is polar? Well, ammonia is polar. So and ammonia is already a gas, so it's not a problem. So what we can form is we can form an analogous compound, but with ammonia instead. So let's squeeze in 3 ammonias in there, in the same spots. Here. And so we just squeeze those in there, into the gaps between the ions. And then, chlorides are all soluble. Chlorides are all soluble except for which ones? Which 3 chlorides are insoluble? Silver, lead, mercury. Silver, lead, and mercury. So both these, the hydrate and the ammoniate, are going to both be soluble in water. So when we dissolve these in water, let's say now it's not H2O gas. I'm going to just dump this into H2O liquid. Now, soluble salts are strong, weak, or non-electrolytes. Soluble salts. Strong electrolytes. So strong electrolytes do what? They dissociate or break up into ions. So we're going to have cobalt-3 plus 3 chlorides plus 3 waters. And these 3 waters are going to join all the other waters in the aqueous solution. The same thing here. If I take the ammonia analog, I'm just going to get cobalt-3. I break apart the lattice. When I break apart the lattice, the ammonias that were trapped in the lattice are now free. And we call that free ammonia versus, and the same thing, these are free waters they're going to add. The free ammonia is just going to add to the rest of the solution there. Okay. So we can test how much chloride. There's a simple test for testing. Chlorides are all soluble except for silver, lead, and mercury. So one of the simple tests is I just add some silver nitrate solution. Nitrate salts are all soluble. So I add some silver nitrate, and what am I going to get? I'm going to get a precipitate of silver chloride. How many moles of silver chloride will I get for this? I should form 3 moles of silver chloride because I have 3 moles of chloride. Or, for every one of these that dissolve, I should get 3 chlorides, and if I get 3 chlorides, I get to get 3 silver chlorides. Make sense, basically? And the same thing with the ammonia complex here. When I add excess, this is excess silver nitrate, I expect how many to precipitate out? I expect 3 to precipitate out. Okay. This is expected. But do you know what was observed? Observed, it would be nice if it were 3. But do you know how many were observed? 2. So there must be a mistake. So yeah, people are thinking there must be a mistake. And so if you suspect there must be a mistake, then what do? You retest it, you repeat the experiment. It's got to be reproducible. You need reproducible results. And so this is why when you write your observations, you have to write enough detail in your observations so that somebody can repeat the experiment exactly the same way that you did it and get exactly the same results, and then you know it's reproducible. You know. Unfortunately, there's, just the way science works, there's cheating in science too. I was looking at this one paper, and this one paper was coming up with some ridiculous results. There was no way that they were going to be reproducible, but it's this kind of publish or perish thing. I guess there's so much pressure on it. And so there's some complaints about people publishing things that clearly are not reproducible. And so you got to watch out. These are in refereed journals. Refereed journals means there are people that review it. You have to watch out. And so this reproducibility is really important. It's crucial. But anyway, this was reproducible. And not only that, many, many different groups got the exact same result. So there's totally something wrong with our calculation or with our understanding of the structure. Which would you blame? Understanding of the structure. So here's our observations. What comes next? The pattern. Well, this is a reproducible pattern. Because if we take the ammonia analog, you know how many silver chlorides precipitated? 2. Only 2. So we got a pattern there. And then oh, this is wrong. Shoot. Let me redo this. Observe 3. Here. This was observed as 3. So this is right. But this is the weird one. This is only observed 2. So I need to correct that in the morning class. And so we got some kind of pattern, and then what do we come up with? A theory or a hypothesis? What comes first, a hypothesis or a theory? Hypothesis. So Werner came up with a hypothesis that the structure is not like this. The structure for this should be written. So cobalt 3 chloride dot 3 NH3 should really be written like this. It should really be written cobalt NH3 3Cl. So we're doing it alphabetical here with name. You could do it alphabetical with formula N and C, so you put the Cl first. It's fine. Cl2. So this is the solid. It's a chloride salt, so it should be soluble. And when you dissolve this chloride salt in water, H2O liquid, what we end up with is this cation. And this chlorine is not ionically bonded, but this chlorine is covalently bonded, cobalt. and 2 chlorides. Mm-hmm.
But how can people predict when, like, it's gonna act as a Lewis base instead of forming an ionic structure?
Because how can you predict? Because in general, all of these will act as a Lewis base, all of them. And we look at how good the ligand is. Like ammonia is a pretty good ligand, so ammonia will displace chlorine. So if I put, this is it. If I put 4 ammonias in here, do you know how many chlorides I'm going to get? So if I throw in another ammonia, what that's going to do is it's going to kick out the chloride, or the chlorido. And so I'll get 3 chlorides, and I'll get 3 moles of silver chloride precipitate. And so they all do that. In other words, they all form ligands. They're all attacked like that. Even in this, what happens is these waters, they don't go in these random interstices. Well, new structural studies of that show that these waters actually attach to the cations in here and form a hexa aqua or tetra aqua cation, which is going to be surrounded by the anions. And so the cations in these lattice structures are actually coordinated. I didn't talk about that in 1A. But anyway, this is the hypothesis. The hypothesis is we have complexes that can form. And so we talked about it. And this came out to be widely accepted. When it becomes widely accepted and can make predictions, we just made a prediction. What if I throw in another ammonia in here? Ammonia is a better ligand than chloro. So the chloro gets kicked out, ammonia replaces it. That's called what? It's called blank, blank. It's called blank exchange. Ring a bell? It's called chemical exchange. Does that ring a bell? So I was talking about chemical exchange, and I was talking about the chelating and all that. I don't know if do you remember that? Well, anyway, this comes out, it's widespread acceptance, we can make predictions, and we have Werner's theory. Werner's theory of transition metal complexes. TM for transition metal, and then complexes. And do you know Werner won the Nobel Prize for this? So he got the Nobel Prize. Otherwise, the observations were very confusing. Yeah. Okay. So I screwed up on, I just copied and pasted this, so I don't know, there was a typo in there. Sorry about that. Just realized that now. Eight, what is the coordination number of that? Well, name that. Can you name that for me? Close. That was close.
Dichloro, diethylene, diamine, platinum 4.
Close, but not quite there. Yes, that's it. Dichloro or dichlorido, bisethylene diamine, platinum 2. We wouldn't use platinate because it's just a neutral complex. This is a complex compound. And what is the coordination number for this? 6. Because these are bidentate ligands. So we have 2 bidentates, it's 4, and then 2 monodentate ligands, 6. It's octahedral. Platinum 2 complexes are usually square planar. And platinum 4 complexes are normally octahedral, but those are all rules with lots of exceptions. What we need is more theoretical approach to it, but we just look it up in the table. Which is expected to be the strongest ligand? Hydroxide, carbon monoxide, chloride, ammonia, or water? Carbon monoxide, yeah. Carbon monoxide is very deadly. Do you know what the OSHA limit for carbon monoxide in a room is? It's like 8 ppm or something like that, or 8 ppb. No, I think it's 8 ppm. So in an 8-hour period, you can't exceed 8 parts per million. That's very little carbon monoxide, at the part per million level. So it's extremely toxic. Hydroxide is extremely toxic too, but how toxic is hydroxide? I mean, there are people who drink like pH 9 water. I saw it, pH 9 water. That's really basic. It's got a lot of hydroxide in there. It tastes slippery, it's probably good. It's alkaline. Alkaline water, alkali is hydroxide, alkaline, right? Or alkaline, hydroxide. But carbon monoxide is quite toxic. Chloride, not really. Ammonia, weak. Water, no. So carbon monoxide. But what makes carbon monoxide such a powerful base? It's got an unusual Lewis structure. What was unusual about carbon monoxide's Lewis structure? Negative formal charge. This is going to be carbon-oxygen triple bond. Carbon wants 4 bonds, so there's got to be a lone pair here. When we have a lone pair and 3 bonds on a carbon, it's negative charge. Natively charged carbon is very reactive, extremely reactive. That acid chart here, the strongest base on this chart is this one here, NH2 minus. NH2 minus is called amide or amide. That's the strongest base. It's a bit stronger than hydroxide. Actually, this chart's wrong. I tried to fix this chart, but sulfide is mispositioned. Sulfide is a more powerful base than hydroxide, and so this is me. I tried to draw this line because this is the wrong value here. It should be 10 minus 19. So I tried to fix that. That was known since this chart was published 1998. This was known like in the 70s or 80s. They figured that out. So they're using old data for that chart. But that's not the strongest base on our chart. What is the strongest base on our chart? Have you even looked at our chart recently? Does anybody know the strongest base on our chart? Yes. When we look at our chart, and this is why I say, if you read the entries in a chart, you're already well ahead of everybody else. Because how many people actually read the entries in a chart? Most people look at the chart and they see a jumbled mess of data. It's too much data. Too much data, and so that's typical science. Typical science is you get a jumble of data. You look at that chart, it's too much data. And so what we got to do is we've got to reduce the data. Have you heard of data reduction? Data reduction is very important in science because we need to reduce the data into simple patterns or something else, to make it easier. In the process of reducing the data, the first thing you got to do is just read the chart. You read the chart to look. Well, this chart has already been reduced because it's already organized in a way. But we'd reduce it further because this is too much. People ask me, do I have to memorize this chart? No, you don't have to memorize this chart, but you should at least read it once in a while, so that you know what's on it. So this is why I was asking. I was asking you to give me a better reducing agent than lithium, or not a better one, a weaker one. A weaker reducing agent than lithium, or a weaker oxidizing agent than oxygen. And so sometimes if you read the chart once in a while, something might stick in your memory, and then might be able to answer that. And so I was looking for any of these metals. So I was asking what's weaker than lithium. Well, I was hoping you'd give me any of these other metals here. But somebody did, aluminum, I think, which was good. Well, once in a while you should read it. And people have these 7 common strong acids memorized. Do you have these memorized here? But I don't know why people don't ask to memorize the bases. I have the bases memorized. So what are the strong bases? The strong bases are these are the strong bases here. And what is the strongest of the strong bases? Methide. CH3 minus. See, this is carbon with 3 bonds, 3 single bonds in this case, and it's got to have a lone pair. That's going to make it super reactive. And so this is methine. So once in a while you just read it. And then go from there. But do you know how to name these? This one should be easy. What's the name of that? Oxide, hydride, methide. Do you see all those end in IDE? And usually it's the element, like hydride. But when we have like ammonia, we'll just call it amide, like ammonia, anion, amide. And this is like methane, anion, methide. So that's the origin of those names, amide and methide, or amide and methide. So going back to this, out of all these, this one stands out as being unusual. You know, it's got the weird Lewis structure and it's got a negative on the carbon, making it quite reactive. You know. Much more toxic than carbon dioxide.
So just to be clear, what makes a strong ligand is a super reactive base?
Yeah.
Okay.
Yeah. Super reactive Lewis base. However, it's not a very good Bronsted base. No, it's not a great proton. It could accept a proton, you know, but they're better proton acceptors. All right, 10. Name that. What is that called? Yeah, diamine silver 1 ion B. Sometimes you could do things by process of elimination. So this is an anion complex. Anion complex, do we call it gold, goldate, or orium, or orate? Orate. And so if it's orate, then we just eliminated all these. And so it's either A or B. And so the difference is the charge. What's the charge on gold? It's got to be +3, so it's A. You know, so even if you don't know the name, there are certain things in multiple choice. You know, that's a common tactic. Just eliminate the ones that are clearly false. Okay, name this. So here's an example where we have a complex cation combined with a complex anion. So everything in the complex is covalently bound, everything in this complex is covalently bound, and then we're going to have an ionic bond between these two complexes. Ionic bonds aren't shown with a line, you just put the cation next to the anion, like sodium chloride or something like that. And so what did you get for the name of this? Yeah. Tetraamine copper 2, not cuprate, we can eliminate that. And these are clearly wrong, the ligands come first, so it's there. And so we have a choice here. It's either tetracyano diaqua ferrate 2 or diaqua tetracyanido ferrate 2. So what do we do when we name it? Alphabetical. And so this one I thought was fair because it doesn't matter. I mean, whether you do it by a formula. Actually, it does matter. In the name, it's always the alphabetical order. In the formula, based on the name. In the formula, it could be the alphabetical order based on either the element, symbol, C before H, or the name. And so what they did was, I just copied this and pasted it, like what I did with the other ones. I just copied and pasted it from our book. So this one could be flipped too. You could put the aqua before the cyanide in the formula. Oh yeah, right. There should be an extra M in the mean, so we could eliminate this one too. And so it's going to be that. There should be 2 M's.
So would you hear arguments for D if there were two M's in the mean?
If there are 2 M's in the mean, then D or E would be correct. I'd take either. If there's only 1 M, well, actually, cyano's still aqua versus cyano. Aqua would come first still. So the alphabetical thing would still occur here. But if there are 2 M's here, yeah, maybe, I don't know. So I try to pick examples. So I think I now remember, I only put 1 M here to steer you to E. So we don't have to have a debate about alphabetical based on element, symbol, or alphabetical based on name. Okay. All right, any questions on this? All right, this one was worth 24. The typical test is going to be worth 50 points, but this is just part of chapter 24, so that's why the points didn't come out there. And we're also going to have a lot of points this semester. We should have, roughly 1,000 points altogether.
Will we get a practice one for chapter 16?
Will you get a practice one for chapter 16? Yes. Maybe I'm either going to give it as a quiz. I'll probably give it as a quiz. So you can see. We'll do that maybe tomorrow. Tomorrow, Thursday. We're going to have the chapter 16 because we're finishing up chapter 16 today. So if we finish it up today, then we're going to have a chapter 16 test next week. Probably on Wednesday next week. That means the chapter 16 homework will be due. I forgot that, the chapter 24 homework, there are all kinds of problems with the name, I think. And so if you feel you're unfairly deducted, I just copied the scores off Mastering Chem, but if you feel it was unfairly deducted, you can let me know. I'll correct the score. Normal homework assignments worth 10 points, but this particular one is only worth 4.8, so I made it 48% chapter. I think we have like 3 or 4 more sections to cover. All right, so let's continue with chapter 16 then. There are no more questions here. So we have the equilibrium law, right, K. And so what we want to do is we want to figure out all the ways to determine K. And so one way we can determine K is experimental. We just measure the equilibrium concentrations or the equilibrium pressures, and then plug those into the K expression. But experimental requires a lot of work. You got to set up the experiment and you got to take the measurements. And sometimes taking the measurements for the concentrations isn't so easy. How do you analyze what the concentration is? Do you do a titration? What do you do? So we try to avoid experiment, and we try to calculate it. And so far, the way our calculations have gone are like a Hess's law style calculation. It's not Hess's law. Hess's law is for like energy. And when we combine equations, we add the energy. When we multiply equations, we multiply the energy. But for this Hess's law style calculation for K's, we combine the equations. What do we do with the K values? Do we add the K values, or do we do what? We multiply the K values. Or if you multiply the equation, then do you multiply the K value, or do you, no, we raise it to some power, whatever you're multiplying it by. So the K value is going to be raised to that power. So when I say Hess's law, it's not like Hess's law. It's Hess's law style type calculations, where we're adding it to get the net reaction. And so that saves us work. If we have data that we can use from existing reactions in some database, then we can figure out, K for an unknown reaction using that without having to do experiment. So we can calculate using existing Ks. The other alternative is to try to calculate it theoretically. Using thermodynamics. Thermodynamics. This is going to come later on. Save this. All right, so this is K determination. What do we use Ks for? And so K application. The main application for K is just to do stoichiometry calculations. What we want to do is we want to determine the equilibrium, concentrations, or equilibrium pressures. Look at this. And so there's relationships between pressure and concentration. That is Kp and Kc relationship. Okay. Which one do we use? KEQ, PEQ? Depends. And sometimes they're the same. They'll result in the same stoichiometry. Other times they're different. All right. Actually, they're different. Different units. And sometimes the Ks are the same. And so remember Kp and Kc? This equation, Kp is equal to Kc times what? RT to the delta N of gas. This equation isn't so difficult to derive. You could derive it if you forget it, or look it up, or memorize it. You're not going to have it memorized. I'll give it to you if you need it. I'm sorry? delta N of gas. If delta N of gas is 0, let's say you have 2 moles of gas on the left, 2 moles of gas on the right, delta N of gas is 0, there's no change. Then Kp and Kc are the same numerical value. They're the same numerical value, but they mean different things. For Kp, you got to use the Kp, you got to use the pressures, not the concentrations. Kc, you got to use the concentrations, not the pressures. Mm-hmm.
The equation on the textbook uses like Pc to the power C times Pt to the power B, which is like the product over the reactants.
Mm-hmm.
And then 1 over P naught, which I guess means 1 bar, to the power of delta V, which is delta N.
Yeah, the book, it depends on how you derive it. I did a very simple derivation of this. You know. The derivation is based on the ideal gas law. Remember from chapter 6, P is equal to the molarity times RT. The molarity is the number of moles over the volume. So P is equal to N over V times RT. In other words, P is equal to nRT over V. And so this is where I come up with the equation from. We have the delta N in gas terms there because the units not cancel between the numerator and the denominator. When the units cancel, then they're the same thing. That's another way of thinking about this. But anyway, we have the stoichiometry. Now, some of the hardest things in this chapter, chapter 15, or is this chapter 16? Chapter is this 16. Some of the hardest things is the algebra. And so this is why I did the method of successive approximations for that problem. We had to use that. Unless you had a cubic, but I didn't even want to get it in cubic form. That would have been just too much. And so let's take a look at some of the homework problems. So the order, for me, what's most important if you're studying, number one, the notes. Make sure, when you go into a test, make sure everything makes sense. If there's something confusing in the notes, get it cleared up. You know? Preferably get it cleared up well before the test. The reason why you want to get it cleared up well before the test is because it takes time. It takes time to. I did some studying about this because I was trying to figure out how to study, and so it takes time to build these neural connections. So each neuron, how many other neurons is it connected to? And so that's it. And it takes time to build that spider web of connections. And so this is why, when I say read it, I didn't just read it once. When I had a table like that, I'd read it like every day. If you read it like every day, then it's like, if you drive to school or something, it's kind of complicated. You pass by lots of different things, but if you see it, every day, then it becomes more and more routine. It takes less and less brain power to think about it. But so I think number one, for preparing for tests, I would go through the notes, and if I do a calculation, like, have you repeated my calculation on your own with a blank sheet of paper? Yes? If yes, then good. If no, then bad. And then if you repeated it, how many times have you looked at it again? You looked at it a bunch of times since then, that's good, because it becomes less and less brain power to think about it, figure it out. And so I would do that. Look at the calculations we do in class and make sure you can do all those. And then move on to the homework. The homework is next. But the homework I don't do once. And I really didn't really do it. Because I did some of them, but I didn't do all of them. I kind of just copied it. I copied because I had the solutions guide. And so some people call it cheating, looking at the solutions guide. I did it regardless. Some people say, you know, you can really help yourself by figuring out yourself, you know, but sometimes it takes too much time for those neural connections to build, right? And so what I needed to do is I needed to rapidly build those neural connections, the spider web in my head. And the way I could do that the fastest was not to, you know, this is what I literally do. I'd like bang my head against the wall trying to force the things into my brain, right? It wasn't working, you know, it was working too slowly. You only have 10 weeks on a quarter system. 10 weeks goes by very fast, you know, it's like 2.5 months. 2.5 months and then your finals. The finals is 11th week. I didn't have time to wait. So that's what I did. And not only that, I went through the homework problems to try to build that spider web of connections by reading the homework problems daily. So I read my notes daily and I read my homework problems daily. Sometimes I looked at the table daily. Sometimes not. Depends if I thought it'd be useful or not. So make sure you can do the calculations for next test. So let's scan some of the homeworks. And then we're going to look at some of the problems here. Equilibrium constant expressions is products over reactants. There's a Kc. Kc is for molar concentrations. Concentration of products raised to the respective coefficients divided by the reactants. Kp is for pressures. It's fine. What's KEQ for? Equilibrium. And what do we use? Concentrations or pressures? Or activity? KEQ we reserve for activities. So this is Kc, NO squared divided by NO squared, NO2 squared divided by NO squared divided by O2. Those are the expressions. So we get some practice writing out the expressions. Here's relating Kc and Kp. We'll just use the equation. Here's Hess's law. So when we add equations, what do we do with the k's? Multiply the k's. Sometimes we have to reverse them. Sometimes we have to multiply by a coefficient. And change that. So this is all Hess's law. Here's determining K. This is determining K from experimental data. And so they give us enough information. You know, at equilibrium, we have this many moles, so we can figure out, okay, we can figure out how the molarity, or we can figure out the pressure at equilibrium. So we have enough information. They want the molarity. So we have enough information to get the molarity concentrations of all the species using a little bit of stoichiometry. They don't give it to us, you know, so it's not, so we have to use a little bit. Because they say is introduced. If this many moles of PCl5 is introduced, that means is that the equilibrium amount or the initial amount? That's the initial amount, so we have to figure out the equilibrium amount of PCl5. And we can do that using a little bit of stoichiometry, like we did earlier. And so these problems are all very similar to that. They don't make it super simple, but it's not super difficult. Here, you know, this type of situation comes up, you know, here. Like, write the equilibrium constant expression for this. So this is just K, so I assume this is a KEQ. So when we have a KEQ, we use the activities, but we aren't going to go to the activities. We're going to just assume that the activities are close enough to what? And so the activity of iron 3 plus AQ is just going to be close to the what? The molar concentration of iron 3 plus. So it's just iron 3 plus raised to the first power. The activity of H2O liquid is what? 1. So we just write 1 there. So this is concentration of iron 3 plus to the first times 1. And normally we don't even bother writing it in there. Divided by, now this is a problem here. What's the problem with this?
You know,
There's no state. We forgot to write the state, and so it got accidentally deleted there. So I should be more careful. But these kind of things are quite common. I mean, this is the 12th edition. You think by the 12th time they went through this, they would have caught it, but they didn't. Yeah.
solid?
Hmm?
Isn't it a solid?
It's a solid. So a solid, what's the activity of a pure solid? One. So this doesn't even go in. You know, if this were aqueous, then for sure it would go in. But we know hydroxides. Hydroxides are all insoluble except for which ones? Group 1, ammonium, and calcium, strontium, barium. And those hydroxides also correspond to the strong bases. You know? The soluble hydroxides are all strong bases. They produce a lot of hydroxide in solution. The insoluble hydroxides are weak bases. You know? They just don't produce much hydroxide. And so this would be a solid. These solids, insoluble salts, do not ionize or do not dissociate in water to any significant extent. So this would be just a weak base acid. This is just Brown-Stitt acid-base reaction here. The next thing we look at the magnitude of K. Is this favorable or unfavorable reaction? Does this have a driving force? When I look at the K value, I'd say yes. Why? Because it's kind of big. You know, 10 to the third. 10 to the third is kind of big, which means it favors the product or it favors the reactants? It favors the product. Yeah. We can't do this outright, but you know, to the first approximation, we could say it's like a 9,000 to 1. 9,000 product, 1 reactant. So product totally dominates 9,000 to 1, right? We can't do that outright because the numerator is linear. However, the denominator is cubic, you know, and so it's nonlinear. And so it's tricky, but still it favors the product. When we look at the magnitude of the K values, the magnitude of the K values vary a huge range. When things vary huge range, like orders of magnitude range, then what we like to use are power functions, like the Richter scale. Richter scale is a power function, right? And the same thing with something like this. We see a huge range, like many, many orders of magnitude. And so the power function of this would be like 3. You know, that's the power. And so we'd say this is around 3. And we call it pK value, power of K. It's 3. It's almost 4 because this is close to 10 times 10 to the third. 10 times 10 to the third would be 1 times 10 to the fourth. So it's between 3 and 4, the power function. Here. Uh-huh.
So when finding a K, we have to do the products over reactants.
Yeah. K is always products over reactants. So this is one of the most common power functions that we encounter, and that is the power of the hydrogen ion concentration. And so when we look at the hydrogen ion concentration, hydrogen ion concentration is 1 times 10 to the minus 7. So the power of this is 10 minus 7. But for the P, we invert it. So the P is going to be negative of the power. And so the negative of the power is negative 7, which gives us a positive 7. So it's flipped. So the pH scale is flipped. And that's what's typically done. It's flipped. And so what this means is it's kind of weird. A pH of 7 would be 10 to the minus 7. You know, a pH of 5 would be 10 to the minus 5. 10 to the minus 5 is 2 orders of magnitude bigger, which is 100 times. You know, power function of 3, a pH of 3 is 4 times more acidic. No, it's not 4 times. It's 4 orders of magnitude times more acidic. In other words, 1,000 times more acidic. No, not 1,000, 10,000 times more acidic. Does that make sense? Goes by powers. So a pH of 1 would be how many times more acidic than a pH of 7? A pH of 1 would be how many times more acidic than a pH of 7? 10 to the 6, which is 10 to the 6 is a million times more acidic. So a pH of 1 is a million times more acidic than pH of 7. Because it's 10 to the minus 1. And so that's a power function. This is the most common power function. when we measure pH, we're measuring the equilibrium. So we're measuring the equilibrium H plus, and then this is an easy way. So if H plus is in there, we can determine what the concentration at equilibrium of the H plus is by putting a pH meter there. And once we get that, we can figure out what the concentration is. And so, that's how you figure out what the equilibrium concentrations are experimentally, but it still requires an experiment to do this. But we have the K value. That's to determine the K value. That's one way to determine the K value. In this particular problem, what are they asking for? Write the equilibrium constant expression. Okay, that's not a problem. And compute the equilibrium concentration for iron 3 plus at pH 7. So they're asking us to compute the equilibrium concentration for iron 3 plus at pH 7. So what does that mean? pH 7, is that our initial pH or our final pH? Initial? So you start off initially at a pH of 7, and then you go ahead and let it equilibrate. And what's the final pH? Is that it? Or what's the final iron? And so we have to be careful. They say compute the equilibrium concentration for iron 3 plus. So we want the equilibrium concentration of iron 3 plus at pH 7. So the pH 7 must be concurrent, or they have to be, in other words, at the same time. And so this must be equilibrium. So if it's equilibrium, then this problem is very easy, This problem turns out to be, we don't even need the ice table. Most problems we need the ice table, but if we're given the equilibrium concentration for this, then there's only one unknown. And so let's take a look at this one quickly here. This one. So I think that was number 71 or something like that. I'm sorry? 21? Okay, number 21. Thanks. So we need to always be asking ourselves, is that equilibrium or is that initial? Do you guys remember Q? I should add that up here. When we're doing these, we always calculate Q as well, but not always. Q tells us direction of change. Q is the initial over the initial products over the initial reactants raised to their respective power. So if Q is equal to K, there's no change. It's already at equilibrium because we're looking at initial and comparing it to the equilibrium. If Q is less than K, then there's not enough product. We expect the change to be left to right. If Q is greater than K, there's too much product, and therefore we got to get rid of it. So the change is right to left. So we calculate Q. But here we're given not the initials, we're given the equilibrium, H plus. We need to cube that. This is the equilibrium. And so we're given K, so we know what K is. We're given K and we're given the H plus, and so we just solve for this. So we didn't even need an ice table because we already have the equilibrium. Ice table, you can still use for this. It's a good idea to do an ice table for all the problems, especially when you're learning, but we could have saved a little bit of time here. Dissolution. 57.5 means what? 57.5 means we have significant quantities of reactant and product. It just slightly favors the product, but not by much. 10 to the minus 9. Oh, that's molar.
So like the closer it is to 0 is the closer, or like the more equal the products in the reactant.
The closer it is to 1.
1, okay.
Right. The closer it is to 0, then it's going to favor reactants more. So you go to smaller and smaller numbers. Like, look at this one. This one's minus 10 to the minus 2. This is going to favor the reactants. So we could do ice calculation. Look at this one. This one is 10 to the positive 19. So people want to save space. So if you want to save space, we can write these as pK functions. pK functions, you can get rid of the scientific notation. This would be 19 point something, or 18 point something, or 20 point something. But this heavily favors the product. Here, sometimes we use fractions. We use fractions if we want to normalize it per mole. So per mole of ammonia. And look at, this is the combustion of ammonia. This combustion of ammonia produces nitric oxide, but combustion can produce a mix of oxides. We could get nitric oxide, we could get nitrogen dioxide, we could get nitrous oxide. And so we call those NOx. And so it doesn't always burn so clean, but in this particular case, we're just burning it to nitric oxide. When we look at the decomposition of NO2, it's 0.524. So we're going to see K values all over the place. It's a bunch of calculations. Direction and extent of chemical change. Direction is Q. We need to know, is it already at equilibrium, no change? Top heavy, too much product? Or bottom heavy, too much reactant compared to equilibrium? So that gives us the direction of change. Extent of chemical change, we just do the ICE table. Extent of chemical change, we usually look at percent. How much did we lose in terms of percentage? That's the extent. Did 50% of it react? 100%? What happened? And so we have different K values here. 31.4 at 588 Kelvin. K values change with temperature. And so that's why we need to specify the temperature. This one's at 445 degrees C. Can you see why there's no standard thermodynamic temperature? There's no standard thermodynamic temperature because we do chemical reactions at so many different temperatures. That to pick a temperature like 0 degrees C, even to pick room temperature, if you're going to pick a temperature, you might as well pick room temperature because most people don't like to have to heat things up and cool things down. And so we just use room temperature. But none of these are room temperature. 248 degrees C, 668 Kelvin. Oh, this one might be room temperature because it's not specified. If temperature is not specified, then it's likely room temperature, unless they made a typo and forgot to include that in there. Oh, did it? Oh, all right. 250 degrees C, 1,000 degrees C. I don't know. We'll come on. And so we're going to do a reaction here. I'm going to show you some tricks to use in ICE calculations that make the algebra simpler, hopefully. And what that means is that it won't be as difficult to calculate. And so I'll show you a couple of calculations for that. I'm going to come back to these here in the 40s. Sometimes, going back to redox reactions here, sometimes the oxidizer and reducer have complicated formulas. So sometimes we use these abbreviations like NAD for the oxidizer and NAD. Oh, they're calling this the oxidizer, this one's the reducer. And they have different forms. Actually, the formula is different. So usually they call this NADH. H for the reducing form and NAD for the oxidizing form. Le Chatelier's principle. We're going to do a quantitative example of Le Chatelier's principle, but first I want to show you some tricks here for this. And so we're going to go to here. Reactions with very small or very large K values. When we have reactions with very small and very large K values, then we start to worry about something. One of the things we start to worry about is how many digits does your calculator carry? Do you know how many digits your calculator carries? I know how many digits my calculator carries. My calculator, my Casio FX115 carries 10 digits. Why would I even care if it carries 10 digits? Why I care is because what happens if I have 11 digits? What does my calculator do? Does it crash? Does your calculator crash? You put in 11 digits? Or what if you have like 30 digits? Are we out of time? 5 minutes? Okay. What happens is it doesn't crash. What does it do? If you put in 11 digits and your calculator only carries 10 digits, do you know what it does? It rounds it. And so what we worry about is rounding error. That's why I care. Do you know how many digits Excel carries? You think Excel carries an infinite number of digits because, you know, I got an i7 processor here. It probably can handle infinite number of digits. Do you think it can handle an infinite number of digits? No. Do you know how many digits Excel carries? It carries 100 digits. Hopefully that's enough, you know. But I'll tell you, 10 digits isn't enough for us. In some calculations, it's not enough. And so what happens is we get an error. It's called round-off error. And it happens especially when we have very small and very large K values. You have to be aware of this. And so let's talk about this. This is very small. 10 to the minus 16 is quite small. And then we're going to go to this one here. The equilibrium constant for the following reaction has been estimated to be a K value of 10 to the 20 at 25 degrees C room temperature. Estimate the equilibrium concentration of this. What's the NH2 minus, Helen? Amide. In a solution prepared by dissolving 0.0125 moles of sodium amide in water to make 1.00 liters at 25 degrees C. Is a result physically meaningful? And so what I want to do is I want to talk about Ka and Kb right now. Amide is a strong base, correct? And what do strong bases do? They hydrolyze water completely. And this is the opposite of strong, well, that's not really the opposite of strong acid. What do strong acids do? They ionize or hydrolyze complete. So if they ionize, let's take HCl. An example of this is HCl. HCl ionizes completely into what? H plus and Cl minus. Or HCl hydrolyzes completely. If it hydrolyzes completely, then hydrolysis, hydro is water, lysis is break. So we react it with water, and we're going to form what? Hydronium and chloride. So if we look at the K for this, the K for this is H plus times chloride concentration divided by the HCl concentration. And we call this Ka. This is called the acid ionization or acid hydrolysis constant. Acid ionization or hydrolysis constant. In this case, it's the acid ionization constant. Whereas, what's the Ka for the second reaction? The Ka for the second reaction is going to be hydronium times chloride divided by the HCl. And what's the activity of pure water? 1. So, and take a note, hydronium and the hydrogen ion are the same thing, essentially. So these are equal. And so this would be the acid hydrolysis constant. And they're the same thing, basically. Now we have bases, and so we have, well, actually we have a table of Ka values, and if we look at the Ka value here, if this ionizes 100%, what's my equilibrium concentration of HCl? If this ionizes 100%, then I ionize all of it. And so if I ionize all of it, how much am I going to have left over? 0. So in equilibrium, I expect HCl concentration to be 0. If this is 0, then what is Ka? It's undefined, right? We call it approaches what? Infinity. It approaches infinity. So let's take a look at our chart of Ka values here. You go to HCl. HCl on the right, the very right column here are the Ka values. Do you see the acid ionization or the acid hydrolysis constant there? What is it for HCl? What's the number? Very large. Too large. Do you have a very large key on your calculator? You don't have that key on your calculator, so how are we going to do the calculation? Well, if the Ka is very large, you know what? We just say, screw the calculation. This is very large. And then we assume, if it's very large, we're just going to assume 100%. But they shouldn't say very large. They should just say infinite, infinity. Infinitely large, right? That's what they should say. But they're just going to call it very large. It turns out it's not as large as you might expect. Okay, now I'm going to talk about the conjugate relationship. So this is what we call the acid here, and this is the conjugate base. And this is what we call a conjugate pair. And this is another conjugate pair here. This would be the base, this would be the acid. And so these are conjugates. Now we're going to have an inverse conjugate relationship, or a seesaw type conjugate relationship. So if Ka for HCl is very large, then the conjugate, the Kb for chloride, will be what? Very small. And so there's an inverse relationship there, which we'll talk about, but we're out of time, so we'll continue this next time. What experiment are we doing tomorrow?
Hydrolysis of salts.
Hydrolysis of salts? Okay. Thanks. Just skim through the experiment. We're going to be measuring the pH of salt solution.